ladies and gentlemen, now that we've talked about polar molecules, you see I have on my screen for you our best example of a polar molecule. A molecule, which again is two or more atoms bound together by a covalent bond. We have our perfect example of a polar molecule here in the form of water, where it has a negative end at the oxygen and a positive end at the two hydrogens. Now, the atom around which the electrons will spend most of their time, the electrons will spend most of their time, will have what kind of charge? Remember, electrons are negative, so if they're spending most of their time around this atom, then that atom must too have a slightly negative charge. And that's what we're indicating here on the oxygen. It's going to have a slightly negative charge because most of the electron's time is going to be spent there. Now, in contrast to that, the atom in which the electrons are spending the least amount of time around would obviously be hydrogen in this case. So hydrogen, if there's a less negative charge around as often, it's going to have a slightly positive charge. We call these types of covalent bonds polar covalent bonds because the unequal sharing of electrons generates a polar molecule, a molecule that has a negative end and a positive end. Alright, this is just the water molecule again. The big red one is oxygen, the two small white ones are hydrogens, and you can see the arrows representing the electrons being pulled from hydrogen to the big electron-liking oxygen. Now, in a water molecule, the oxygen has a stronger attraction for the shared electrons. So the shared electrons are going to spend more of their time around what atom? Oxygen. So then the oxygen atom, as a result of having those electrons around it for the extra time, that negative charge around it for a extra time, that atom, the oxygen, will then have a slightly negative charge. So we have our oxygen, has a negative charge. Now the shared electrons spend less of their time around the hydrogen atoms, so the hydrogen atoms are going to have a slightly positive charge. And again, here's hydrogen, and there's its positive charge. One pole, the other pole. This is a polar covalent bond, which is produced by the unequal sharing of electrons. And again, this is just to reiterate that a polar molecule is polar and water is a polar molecule because it has both a negative and positive charge within the molecule. Now, the only way to have a non-polar covalent bond, the only way to truly share electrons, because remember, all atoms attract electrons a little bit differently, like I wrote on the board here that one day. The only way to truly 50-50 share electrons is if the shared electrons are between the same atoms, and they will then be shared equally. As my image depicts here, two nitrogens will share electrons equally. Two oxygens will share electrons equally. And I have some other examples, hydrogen and chlorine as well. They're the same atom, so they attract electrons the same, so it's a 50-50 for the electrons spending time around each atom. So a non-polar covalent bond is just a covalent bond. Alright, it is the perfect equal sharing of electrons. Now, back to water. Water, it's a big deal here. Alright, it's a huge deal when it comes to the chemistry of life. You literally can't, as far as we know, have life without water. And it's that polarity of water, it's that negative end and the positive end in the same molecule that makes water so special. Now we know that in a water molecule, the oxygen atom has a much greater attraction or stronger attraction for the shared electrons than hydrogen. So at any given time, there's a greater probability. So at any given time, there's going to be a bigger and better probability of finding the shared electrons near which atom? Oxygen, because it likes the electrons more, rather than finding the electrons around the hydrogen atom, which likes them much less. So as a result, we know that oxygen gets that slight negative and hydrogen gets that slight positive, and that generates our polarity within the molecule, but that gives water so many special properties, some of which we're going to get to see in class here. And again, remember, a polar molecule is simply generated by the unequal sharing of electrons. All right, this is actually our last bond that we're going to talk about. This bond, we use water as an example, and it's pretty simple. We call it a hydrogen bond. Now, water molecules stick together because of the opposite charges of the molecules, right? The positive end of one water molecule, which is hydrogen, will be attracted, because opposites attract, to the negative end of another water molecule with the oxygen. And we can see that happening here. Look, the red balls are oxygen, the white are hydrogen. This red one's attracted to that hydrogen. This white one's attracted to that oxygen. This white one's attracted to that same oxygen, and this oxygen is attracted to this hydrogen. Okay? These are 4 different hydrogen bonds. Hydrogen bonds always involve the atom hydrogen. Always. So we have our water molecules, we have our hydrogen bonds, and we always represent hydrogen bonds with these 3 little dots because hydrogen bonds are actually weak bonds that are made and broken easily. And we call that force of attraction a hydrogen bond that we see here. Now, a single water molecule as depicted in this image can make up to 4 other hydrogen bonds with other molecules. The oxygen can make 2, and each hydrogen molecule can make 1. So that is 4 total different hydrogen bonds that can be made. Catch you in the next ones, folks.